last thing that we do in this unit. We've spent the entire unit talking about, in one context or another, electric charge. Objects with charge. Where did the objects get their charge? What type do they have? How easily the charges move around versus not moving around, conductor versus insulator. All kinds of different things about electric charges, except what the distribution of charges looks like. The pattern of charges that exist on or in a conductor looks like. Now, I want you to know that everything we're going to talk about over the next 10 to 15 minutes is going to involve conductors, not insulators. If I'm an insulator and I have a big amount of charge built up on me and I touch another insulator, there can be a discharge there. There can be electrons transferring from me to the other insulator. But those electrons that transfer are not going to move around freely on that other insulator. They're going to, for the most part, be concentrated where I touch it. So I'm the insulator. I go over and I touch, let's say, Ed's finger. Makes him sneeze. Develops a charge on him. Those charges are not going to be spread around that insulator, Ed. They're going to, for the most part, stick where I touched it, right? So for the most part, in his finger, in his hand. Make sense? Now, we're not going to talk about that today because charges don't go too far in insulators. What I want to talk about is what happens if I'm a conductor and Ed's a conductor. I've got this big charge built up on me. I touch Ed's finger. I get all these electrons transferring to Ed. And now these electrons, because Ed's a conductor, can move around wherever they want to or need to move around. Where do they go when they're free to move where they need to go? That make sense? Go ahead, question. Yes, they do. They go as far away from possible each other because they repel each other. All of these excess electrons. And now, the other thing is, I should have pointed out, we're not talking about all the electrons in the object, right? We're talking about the excess electrons. Something gets struck by lightning. It has a whole bunch of extra electrons. Something touches another object that has a whole bunch of negative charges. It gains a whole bunch of extra electrons. Everything that we're talking about is the excess electrons, not the electrons that balance out the number of protons, right? So, what does the distribution look like? Hey, Bernardo said, don't they try to push each other away as far as they can? Yes, they try to reach a point of static equilibrium. What does that mean? Equilibrium in physics means balanced forces. They push each other apart until the forces end up balancing out. If you get 20 people in a room, they may not be all that comfortable with one another. They don't know each other that well. Everybody's kind of shy. It's not like everybody's pushing each other away. But in a way we are, right? What do we tend to do? We tend to try to, kind of do our own thing off in the corner, right? As far away from other people as we can. But the problem is, when you move away from one person, you might move closer to another person. At some point, you move around and you find that balance of forces. Now you're in a state of equilibrium. That's what electrons want to do. They want to go as far away from possible as each other, but not too close to the next guy. Not too close to the next electron. When the forces all end up balancing, it's in a state of equilibrium. And that's if we can call it a goal, that's the goal here, is to reach that point of static equilibrium where the forces end up being balanced. So what does the distribution look like when the forces are balanced? Well, I've got 4 shapes that I have drawn on the pages that I handed out to you a minute ago. The first one is a solid conducting sphere. This is a marble, except it's a metal marble. It's a steel marble, a stainless steel marble. It's a copper marble or silver or something like that, right? It's a conducting marble. Take a look at the first diagram here. I have it drawn, or the picture that's on your page has it drawn as 3 negatives. Not 3 negatives really, but 3 excess negatives. I might have 6 protons. I have 9 electrons. I might have 1,000 protons. I have 1,003 electrons. 3 excess electrons. What do? Well, as Ed said, as Bernardo said, they push each other apart as far away as they can go. So let's label these. 1, 2, and 3. 1 is pushed away from number 3. I'm going to call that F31. 1 is pushed away from number 3. Guess what? 3 is pushed away from number 1. I'm going to call that F13. They push each other apart with an equal and opposite force, right? 3 is pushed away from number 2. So I'm going to call that F23. But 2 is pushed away from number 3, so I'm going to call that F32. 2 pushes number 1 away. 1 pushes number 2 away. Now let's look at the net force on each of these charges. Charge number 1 has a net force down here somewhere. Number 2 has a net force up here somewhere. Number 3 has a net force down here somewhere. What do those net forces have in common with each other? The net force on each of these electrons are pushing the electrons where? Outwards, yes, to the outer surface. To the outer surface. So what happens to these excess electrons? They get pushed to the outer surface. If you have extra electrons in a solid conducting sphere, they don't appear on the inside of it. They always go to the outer surface. Now, why do they typically not go beyond the outer surface? You know the answer to this. You get this conducting sphere in air. Why do the electrons not go beyond the surface of this conductor? Yeah. Well, they could go into the air, right? Why don't they typically go into the air? Sometimes they do, but not usually. Why do they typically not go into the air? No. Good guess. No. Good guess again. Nope. You guys are making this more complicated than you have to. All good answers, actually. Okay, there's protons in the air too, though. Good guess. Yeah. Because there's an insulator. Right? If you were to put this in some kind of liquid mercury bath, they would just keep going, right? They wouldn't stop at the outer surface. They would just keep going into the liquid mercury, right? If the air is damp and humid, the electrons would be more likely to leave the surface because the damp, humid air is better conductor, right? So they typically stop at the surface because what it's in is usually an insulator. Okay, let's assume that it is an insulator. Let's assume that all of these go to the outer surface and stop there. Now, if you had 1,000 electrons on the surface, they might be pushing each other apart so hard or so strongly that they just can't hold it anymore. Right? The surface can't hold it in, and they just go into that insulator. So some of them, at least, just go into that insulator. But for the most part, they stay on the outer surface. They stay on the outer surface, and they are evenly distributed on that outer surface. See that? They end up being equidistant apart from each other, evenly distributed on the outer surface. And then, of course, the electric field lines we have drawn in the second diagram, which are toward the negatives, looking something like this. What's the takeaway from this? So you got a solid conducting sphere. Where do the excess charges go? To the outer surface, and they're evenly distributed, period. Next diagram. I don't really even need all three of these diagrams up here. I think the first couple work for us. I'm going to label these once again, these three excess charges as number 1, 2, and 3. I want to focus on the second charge, the middle charge. Number 2 is pushed away from number 3. I'm going to call this F32. 3, it repels 2, pushes it away. I'm going to call this one F12. It's the force of 1 on 2. 1 pushes number 2 away. Why is F12 bigger? Warren, why is F12 bigger than F32? Yeah. Coulomb's law, F is equal to KQ1 Q2 over R squared. If R is smaller, F is bigger. 1 and 2 are closer together than 3 and 2 are, so F12 is going to be bigger than F32. Right there, right? Now what's going to happen as a result of F12 being bigger? Yeah, it's going to move to the right. It's going to move to the right. As it moves to the right, and if it moves to the right, then what's going to happen to the value of F12? As it moves to the right, what's going to happen to the value of F12? It's going to get smaller. What's going to happen to the value of F32? It's going to get bigger. So picture this now. Look at my hands here, okay? One of them's F12, one of them's F32. One of them gets bigger, one of them gets smaller. At some point, watch my hands, at some point what happens? They're equal, right? Then it's in a state of equilibrium. Where is charge number 2 when those two forces end up equaling out or balancing out? In the middle. So what happens to these charges, these excess charges that is? Well, they go to the outer surface again, and they end up being, once again, evenly distributed. When we have a nice uniform surface, like a solid conducting sphere or a nice flat plate like this, they always end up going to the outer surface, and they always end up being evenly distributed. What do we got? Something like this. This is irregularly shaped. I can't even say that word. That's how complicated it is. Irregularly shaped conducting object. Solid conducting object. Yes, you're right. In other words, something that's kind of pointy, kind of pointyish, right? What does the distribution look like then? Well, I'm going to simplify this a little bit by getting rid of one of these charges. We could draw it with 4 charges. We could draw it with 1,000 charges. But it's easier to do it with 3. So that's what I'm going to do. I'm going to label them 1, 2, and 3. I want to focus on number 2. Number 2 gets pushed away from number 1. I'm going to call that F12. Agree with that? Number 1 also gets pushed away from number 2, but I'm focusing on number 2 right now. Now, number 2 also gets pushed away from number 3. That force is going to look something like this. Agree with that? So if I have 3 charges, those are the 2 forces acting on number 2. If I have 14 charges, then there's going to be 12 more forces, but it just makes it more complicated. It doesn't change the result. I want to break F32 up into components. The Y component and the X component. These charges go to the outer surface again. How come? What pushes it? What pushes number 2 to the outer surface? Yep. Not 3 and 1. Which one pushes it to the outer surface? Number 3. Look, the Y component of F32. This force right here pushes it to the outer surface. Make sense? If it's in here, it gets pushed out here by the Y component of that. Got it? Now, what does F12 do? What does Fx do? Well, they're both still on the same plane, right? Which one's bigger? F12. All right. If F12 is bigger, then the charge is going to start moving towards the tip, right? And then at some point, F12 and Fx are going to balance each other out again. When are they going to balance each other out? Well, not when they're nice evenly distributed this time. It's going to be more like this. When the charges are more concentrated at the tip. They're further away from each other out here, and they're closer to each other at the tip. That's why when you walk across the carpet and go to shock somebody, how do you shock somebody? Walking across the carpet, you get this big buildup of charge, and you want to shock. I want to shock Michael here. So what do? Like this. The side of my leg. That doesn't work, right? What do? Point your finger, right? Use your pointer finger. How come? Because we get a higher charge buildup at my pointer finger than I do on the side of my leg or on the side of my hip or on my back, right? Because my finger is pointier than the side of my leg. Make sense? Now, remember, we're not huge conductors, but if we were men of steel, say, Michael, or Iron Man, made out of a conductor, then the distribution would work like that. Does that make sense? To some degree, it works with insulators as well, just not nearly as well as with conductors. Okay? That's why we have lightning rods, right? Why are lightning rods? You guys know what a lightning rod is? See them on the top of a building? It attracts lightning. It attracts lightning. The purpose is to encourage lightning to strike here. We do that because we don't want lightning to strike in random places on a building. We want it to strike here on this lightning rod, which is attached to the ground. So it takes all these electrons from the lightning down into the ground and drains it safely. Why are they pointy, though? Why are they pointy? Because we get a stronger charge distribution of positive at the lightning rod, which encourages lightning to strike there. David? Well, actually, we do conduct fairly well, actually. Yeah, just not as good as like copper, let's say, or something like that. But yeah, we do. Here's the last one that I want to show you today. There's not even much to show you with this. This is almost the same as a solid conducting sphere, right? A hollow conducting sphere. What's the distribution look like? Well, guess where the charges go? To the outer surface. Guess what the distribution looks like? Even. Right? When you have a nice uniform shape, it goes to the outer surface and it's even. It always goes to the outer surface. It's just not always even. In this case, it wasn't even, but here it still went to the outer surface. So what do I want to show you on this? Not how they get to the outer surface, not what the distribution looks like. We already know that. What I want to show you here is the electric field. The electric field you can see in diagram B here is pointing toward the negatives. But let's draw it on the inside of this hollow conducting sphere. There is a field pointing this way towards that negative. Does that make sense? There is a field pointing this way toward that negative. Does that make sense? There's a field pointing this way towards that negative. Does that make sense? Good. What do you think you get if you add these fields together vectorially? In other words, you take the x components of them, add them up, take the y components of them, add them up. What do you think you're going to get? Yes, they cancel. The net electric field inside is 0. We call this a Faraday cage. A Faraday cage. The net electric field inside a conductor is 0. Always. It's not because there's no field, but because the field cancels. That's why a car is a safe place to be in a lightning storm. We have this impression, this false impression, that a car is safe because it's insulated from the ground by rubber. If lightning makes it from the cloud all the way down to your car, you don't think it can make it from the car to the ground? Of course it can. And it does if your car gets struck by lightning. But that's fine, because the net electric field inside your car, which is a Faraday cage, is 0. And if there's no electric field, how are you affected by that? You're not.